In Chapter 15, Section 6, we're looking at surface integrals. Our objectives are to evaluate a surface integral as a double integral and evaluate a surface integral for a parametric surface. This theorem shows us how to evaluate a surface integral. S is the surface with an equation z equals some function of x and y, g of xy, and we project that surface onto the xy plane. We use partial derivatives to evaluate the surface integral. You'll notice the double integral with the s to represent the surface. It is a capital S, and the differential s at the end of the integral. This is translated to a double integral where R is the region where the surface is projected onto the xy plane. So your bounds of integration are determined by the projection of that region. Of the function of x, y, and z, you're going to replace the z in the integral with what z equals on the surface, and you're going to multiply that by the square root of 1 plus the partial derivative of g with respect to x squared plus the partial derivative of g with respect to y squared times your differential area dA. In this example, we want to evaluate the surface integral, the double integral capital S, of y squared plus 2yz ds. That differential s is a capital S there. S is the first octant portion of the plane 2x plus y plus 2z equals 6. We want to be able to write the surface in terms of a function of x and y. So we want to solve for z. You can subtract 2x and y from both sides and divide by 2 to get this z equals 1/2 the quantity of 6 minus 2x minus y. That is our function g of x and y. We want to take the partial derivative of this g with respect to x and g with respect to y, and that's going to be used in our differential s. Also, we want to replace any z in the integral with what z equals on the surface. So by taking the partial derivative with respect to x and y, we get -1 and -1/2. We plug that into the formula here and simplify to get 3/2. This is the surface itself. We're just looking at the region in the first octant. We're integrating across this surface. The projection is in the xy plane, and we want to find the bounds of integration by looking at this dark shaded region in the xy plane. If you set z equals 0, you can see that the plane will intersect the xy plane, and at this equation y equals 2 times the quantity of 3 minus x. Okay, so using that theorem, and we're going to replace any z with what it equals on the surface. You're going to multiply by that quantity of 1 plus the partial derivative squared and the differential area dA. So our original expression was y squared plus 2yz. I replaced the z with 1/2 of the quantity 6 minus 2x minus y. And in the previous slide, when we calculated these partial derivatives and plugged them into this formula, that simplifies to 3/2 times the differential area dA. That base region, you can determine the bounds for y and the bounds for x. The lower bound for y goes from 0 to the upper bound of 2 times the quantity 3 minus x. And your bounds for x go from 0 to 3. Now what we've done here is we've just simplified this equation and in fact brought out that constant of 3. Now you can integrate the inside with respect to y, treating y as a variable and x as a constant, to simplify to get a single definite integral, and then you can evaluate the single definite integral to get the final answer of 243 over 2. So what we've done is we've evaluated a surface integral, moving across the surface, evaluating this integral. Now an alternative solution to this would be to project the surface onto the yz plane. So you want to look at determining bounds for y and z rather than x and y. And also, if you're region is projected onto the yz plane, your double integral should only have y's and z's. It shouldn't have any x's. So we want to solve that original equation for x, and then you're going to take the partial derivative of x with respect to y and z and plug it into the second part of that surface integral formula. And when you do that, you get 3/2 again. Now you're going to replace every x in the equation with what it's equal to in terms of y and z. And we don't have to make any substitution here since the original integral did not have x. Our differential area dA is going to include dy dz or dz dy, and then we would determine the bounds of integration based on the order of those differentials dy and dz. Okay, so when you set it up, you simplify, you get this integral. The differential order is dz dy, so the inside bounds for z go from 0 to the quantity of 6 minus y divided by 2, and the bounds for y go from 0 to 6. And again, you can find those bounds by setting x equal to 0 to see where the plane crosses through the original surface crosses through the yz plane. Evaluate the inside integral and simplify, and then evaluate the single definite integral to get 243 over 2. So as you can see, the answers are the same depending on, for both of those, either projecting the surface onto the xy plane or projecting the surface onto the yz plane. Okay, I'd like you to try this one on your own. Evaluate the surface integral, the double integral for s, of the quantity x minus 2y plus z ds, differential s, where s is the portion of the surface that's bounded by x between 0 and 2 and y is between 0 and 4. You can pause the video, try this one on your own, and then come back to check your solution. Okay, so we have our surface z equals 15 minus 2x plus 3y. That z is the same thing as our g of x comma y equals 15 minus 2x plus 3y. We want to take the partial derivative of this g with respect to x and this g with respect to y. The partial derivative with respect to x, where you treat x as a variable, y as a constant, that partial derivative is negative 2. And the partial derivative of g with respect to y, where you treat y as a variable, x as a constant, that partial derivative is 3. And then that will give us the square root of 1 plus those partial derivatives squared. It's going to be 1 plus the quantity of negative 2 squared plus 3 squared, and that will simplify to the square root of 14. All right, now we can evaluate the surface integral by making substitutions and determining the bounds of integration. For the bounds of integration, we're already given the inequalities for x and y, so we can sketch the xy plane, where x goes from 0 to 2, and y goes from 0 to 4. And this region, the projected region, is a rectangle. So this is both vertically simple and horizontally simple. So we can make the decision whether to use a vertical rectangle or horizontal rectangle to determine our order of the differentials. Alright, so this double integral for surface of x minus 2y plus z, the surface integral, ds, can be written as a double integral r, where this is your region, and you're going to replace any z in the equation with what z equals on the surface. So it's going to be x minus 2y plus, I'm going to replace the z with r, 15 minus 2x plus 3y, all of that ds. Now when we simplify this, we get the double integral And this will all simplify to negative x plus y plus 15. And that ds we're going to replace with the square root of 14 times the differential area dA, where R is that region. And in this case, it really doesn't matter what order to write the differentials for area. We can use dy dx or dx dy. So if we choose the dy dx order of integration of negative x plus y plus 15 dy dx, our inside bounds are for y, and y goes from 0 to 4, and the outside bounds are for x, where x goes from 0 to 2. We can evaluate this double integral by evaluating the inside, treating y as a variable and x as a constant. And that is going to work out as follows. Oh, I forgot to put that square root of 14 in there. We can bring that square root of 14 out in front. Sorry about that. So we can bring that square root of 14 of the integral from 0 to 2. We take the antiderivative of negative x plus y plus 15 with respect to y, and we get negative xy plus y squared over 2 plus 15y, and the bounds of integration, or y equals 0 to y equals 4 dx. So this now becomes, when you evaluate the upper bound at 4 and the lower bound at 0 and simplify, you get the single definite integral from 0 to 2 of negative 4x plus 68 when you simplify. Now you have a nice little single definite integral. You can evaluate that to get 144 square root of 14 as the value of the surface integral. You're integrating throughout this surface, bounded within this region, of the quantity x minus 2y plus z.